Hi. In this example, we're going to try to figure out one of the most difficult things in all of procedural geometry and learning your way through Houdini, which is clearly, in my view, rotations. This is something that we could either struggle with for a few hours or days, or we could struggle with it for a few years. I've seen many that didn't quite understand rotations after a few years, I feel like people could take on more difficult effects if they have more of a command of rotations early on. So this is an area that I really push right from the start is rotations, 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 really trying to understand what's going on in here. So what better way to understand rotations than a bunch of floating boats? So here we can see that these boats are adapting to their terrain and they're rotating to stay above water. And the other thing about rotations that is very critical for any effect is that it really catches the eye. If something is traveling, okay, maybe it's going to catch your eye, maybe it won't. But what really gets the eye is command of like spinny things, vortices. It's really exciting and it'll make your effects more dynamic to really be able to control it better. So here I'm just going to copy the boat geometry. Okay, here's a boat. And I'm going to copy this animated ocean. And we're going to put together a simple effect of a bunch of boats floating on the water surface. So I'm going to Control C, Control V. And let's get started. All right, so the first thing I'm going to do is I'm going to scatter a bunch of points here that represent the boats. All right, so we can scatter. There we go, and that's too many boats. So maybe we want only about 30 boats. Can choose our different assortment, and I'm going to leave the relaxation on just because I want the boats to be a little bit separated from each other. Okay, now because these are being the ocean surface is animated, that's really going to create some chaos for our scatter. So the next thing I'm going to do is I'm going to use the time shift and lock the time above this. So I'm going to set this to the start frame, or F start, $F start. There we go. So now this is time independent. If I middle click, I'll see time dependent no, as opposed to above it, time dependent yes. Okay, so now we have a locked scatter based on our geometry. All right, and just so it doesn't go over the edges, I'm going to finalize this with a transform. And I'm just going to scale this to about 0.9 so that we know that these aren't going to go off the edge of our ocean. Okay, cool. So that part's set up. And when we use the copy SOP, it's going to be dealing with two very key rotational aspects. It's going to be dealing with the direction. So this boat, imagine it looking this way. This would be the direction. We're not going to be dealing in X, Y, Z rotations. That's not how computers or game engines or anything other than hand animating these values deals with rotations. Rotations, as far as the computer sees it, is very much like how we see it in our everyday lives. We see that we are facing this direction and that this way is up. So it's local. These rotations are local to the object. Local to the object in Houdini is facing the Z or Z axis this way. But then it's also important to note that there's another axis in play, because even if the boat is facing forward, what if it's upside down? Well, that's going to take on some water. That's very important to a boat, that it's not placed in the water like this. So we need an additional axis to stabilize this rotation. That could be referred to as a tilt, and it's synonymous with the y-axis in Houdini. So whatever object you're about to copy, face it down the z-axis and make sure that y is up. As a side note, the pivot point at 0, 0, 0 is probably the center of mass. Okay, so we've got our boat. It's facing down the z-axis with y up. We've got our points. And now let's go ahead and randomize the directions. So we can do that with the normal. The normal attribute is going to tell the copy stop what direction is z. So I'm going to use a random number generator. In comes the point number. I'm going to generate a 3D vector. And now we have this. Now they're all pointed down the positive axis. So I want this to be a full assortment of axes. So I'm going to follow that up with a fit. And we're going to fit our 0 to 1 values out of the random to -1, 1. And we can see now we have a truly random assortment of directions. And finally, I want to normalize this, meaning make all of these a unit length. They're all a length of 1 now. Okay, so let's try out copying our boat onto this. There we go. So we see the boat is facing the local z-axis is the normal as it was copied. Okay, so they're facing in the direction we told them to. Now, as I mentioned before, they're pointed in all kinds of different ways. Particularly, some of the boats might be tilted. You see how the closer the axis is to y being up, the more tilted it is. Okay, so first of all, let's just not have them facing up and down. So for that, I don't want any y in the normal. So I'm going to make a constant vector, just a plain number, and let's multiply our resulting fit vector, and we're just multiplying the y by 0 by doing this. There we go. So we've managed to flatten out all of our directions here. Okay. So then what should we do next? Well, next, notice that as our ocean is churning, so here's our boats and here's our ocean. Notice that because we locked our frame, the waves are going over the boats, and that's certainly not ideal. We want the positions of these boats to be following the ocean, right? Okay, so for that, we can use one of the tried and true, most useful nodes in low-level SOPs, which is the ray SOP. Okay, so for here, I'm going to move them up in the air because the next step is going to be to ray them. Okay, so moving them up in the air, and the next step is we're just going to collide them down with our animated ocean, meaning before the time shift. So I'm going to drop down a ray. These are the points that will be rayed, and this is the surface that will be rayed onto. And from here, we have to have once again, a direction, a vector. So here I'm going to say project rays by a vector, and it'll be 0 for x, -1 or down for y, 0 for z. And applying that, now we can see that the boats are rayed to the bottom of what they're colliding with, and now they're adapting to the heights, and they all have random directions. Okay, so we want these boats to tilt according to the water. How would we do that? Well, okay, so for that we need to actually set the up vector, the up attribute. All right, so naturally, any polygonal surface will have polygonal directions. Here, I want to get the direction that this polygon right here is facing, or that this polygon is facing, because then I want the boat to tilt according to that direction. So back up to the ocean here, what we can use is we can use a facet, another very low-level node. Here, there's quite a few low-level nodes in play. Time shift, scatter, transform facet, ray, and copy. Okay, so what's the facet good for? Well, it's good for a lot of things, but I'm going to use it for post-computing the normals. And what that means is I'm going to compute the normal attribute, a point attribute, based on the polygon directions. And now we can see these polygons are adapting. Okay. As we ray this to the surface, as these are getting collided with the surface, I want them to inherit that attribute. But before I do that, I don't want to overwrite the existing normal attribute, because what that did is it set the capital N as well. So I'm going to rename that. There's our attribute rename. I'm going to rename from capital N to UP. There we go. And let's just make a little visualizer for it. Visualize, and it's right here, up. And we can see that we've got our up attribute. Now, as we array the boats, they should inherit that. Okay, and to do that, we would go down here and we say import attribute from the hits, and now it's inheriting that attribute. It's inheriting the up specifically. There we go. So now our tilt will correspond to the polygon direction. And what that's going to cause our boat to do is tilt along with the water surface. Okay, so now you can see that they're facing in the right directions and they're also tilting. Let's address one final issue with this copying. And that's the fact that whenever you do a copy, it's good for your direction and your tilt axis to be a 90-degree angle. And here that's not always the case, because we might have the ocean surface going far one way, and you might create some weird rotations or some problems if these aren't always 90-degree angles. So what we're going to do is we're going to do a cross product. So between any two vectors, there's this imaginary grid. See that imaginary surface that we could paint between all these. And imagine someone standing on that grid. There's going to be this third axis in play. So with a VOP, a point VOP, let's use that axis to make these 90-degree angles. That axis is the only vector that both of these are perpendicular to. So if we were to do a cross product between the incoming normal and the incoming up vector, we should get something perpendicular. See. Now, to align these two, we want now the new vector we just made and the old normal, and then we're going to get a perpendicular axis. So I'm going to do another cross between our new vector and the normal. And there we go. Okay, so now we've successfully aligned these vectors to our existing normal. Okay, so let's export that as the up vector. Up. Okay. Use this node and export when input is connected. It's going to be a vector. There we go. And so that's just probably the most stable way of controlling your rotations. Okay. And we can see that reflected in our boats. Thanks, and I hope that this lesson shed some light on the intricacies of rotations.